All right, we're going to look at some independent and dependent probabilities. So here we go. You play a game that involves drawing two numbers from a hat. There are 13 pieces of paper numbered 1 to 13 in the hat. Each number is replaced. Now, in all these problems, I think the replacement, whether you are replacing or you're not, is going to be the key thing. So each number is replaced after it is drawn. Find the probability that you will draw a 3 on your first draw and a number greater than 10 on your second draw. So first thing, I'm a little bit more visual, so I'm going to write out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I have 13 different options. So that's what my sample space looks like. So what we're going to do is we're going to start off, the first thing it says is find the probability that you will draw a 3 on your first draw. So draw a 3. So first thing we do is what's the probability that we draw a 3? Well, there's 13 total options here, so I know this is over 13. So how many different ways can I draw a 3? Well, there's only one 3 available, so that is a 1 in 13 chance you're going to draw that 3. But here's the deal. So say I draw this 3, I pull it out of the pile. But the question says each number is replaced. So I took out the 3, but now I put it back in. So that 3 is still in our sample space. So now it says on your first draw 3, and a number greater than 10 on your second draw. So everything's back to normal, nothing changed. So now we're just finding the probability that we have a number greater than 10. So we have no type of condition there because I put it back. So I need to find the probability that the number is greater than 10. So I have all 13 options still available. So let's count up how many different ways do I end up with a number greater than 10. Well, that happens if you have 11, 12, or 13. So 3 out of 13 chance. Now what we need to do is we need to multiply those two together. If you multiply the fractions together there, multiply the top, you get 3 times 1, which is 3. Multiply the bottom, 13 times 13 is 169. But if you want to know the decimal equivalent there, 1 divided by 13 times 3 divided by 13, you get 0.017, and we'll round that up to 8, 0.0178. So that is the probability that we draw a 3, put it back in, and then draw a number greater than 10, 0.0178. So let's go to one more problem. So we have a drawer contains 12 white socks and 8 black socks. So I'm going to write that out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And 8 black socks. 1, 2, 3, 4, 5, 6, 7, 8. 12 whites, 8 blacks. We randomly choose one sock and do not replace it, meaning we are not going to put it back. We're going to pull it out and we're going to keep it. Then you randomly choose another sock. Find the probability that the first sock is white. So let's start with that. Probability that the first is white. So let's start with that. The first sock is white. So looking at all these, I have 20 total outcomes available there. And I have 1, 2, 3, 4, 5, 6, 12 options for that white sock. So 12 out of 20 is the probability that I reach into this drawer, pull out a white. But here's the thing. You randomly choose one sock and do not replace it. So that means one of my white socks goes away. So let's move on to the second part. It says, so find the probability that the first sock is white, and, so that means, and we're going to multiply, the second sock is white. But here's the deal. We're going to find the probability that this second one is white, but given, that's what this slash means, given that we already pulled the first white out. So see how that changes from this one to the next one. The big thing has to do with the replacement. Now, you don't need to get all symbols and formula here because a lot of kids, they can just think through it. So let's figure out what's the probability that the second one is white given that I pulled the first one out. So let's count up how many different options do I have here. So I used to have 20, but remember this option is gone. So I'm now down to 19 total outcomes. Now of these 19 total outcomes, because again this is gone, the number that of whites that I have available is 11 there. So see how that decreased because I took that one white one away. Now all I have to do is, since this says and, we got to multiply these together. So in a calculator, you could do 12, division sign 20, multiplication 11, division sign 19. Hit enter and you get 0.347. By the way, just for argument's sake, let's say I did put that white sock back in. So then, if that was the case, if we did replace it, you would have had 12 over 20 for the chance on the first one. But if you put that one back, you would still have all 12 whites available out of all 20 socks available if you replaced it. Since we didn't replace it, we lost a sock. Over here, we did replace it, so we still have the same amount. So you see how those would be different. And that is the probability of independent and dependent events.